Hello, everybody. This is Dr. Ekstrom, and this is the sixth of the 7 video lectures associated with the November 1 workshop on creating content-based digital games on the structure and energy of matter. And in this video, we're going to focus on gases. And so we've talked a lot about uh, interactions, intermolecular interactions and properties that apply to solids and liquids, but gases can be a little different. And so, largely because their energy content is so large that there is not very much interaction at all. And so, and we have additional properties that we can measure, such as pressure and things like temperature and volume uh, can have much larger effects. And so, first let's talk about why do we need to know about gases? The last class I taught had a lot of nursing majors in this, and so it dawned on me that there are health issues that pertain to gas content, gas properties. And so I told the nurses about the medical arterial blood gas test, or the ABG test. And what this measures 3 different things. It measures the oxygen tension, or the partial pressure. What portion of the gas is oxygen? Carbon dioxide tension, how much carbon dioxide is in your blood, as well as the blood pH. And so in order to understand this kind of thing, of course, you have to know what is a partial pressure, and then how is this pressure related to other gas properties. And so I kind of use this to lead into our discussion, and we'll do so here. We know that a gas is gas phase compound will uniformly fill any container we put it in. If you take 2 gases and put them together in the same container, they will completely mix. So whether you have a single substance gas or a mixture of more than one gas, they will all thoroughly fill a container and actually exert pressure on its surroundings. And in the first workshop I talked about this, how can we prove to students that gases consist of particles? Well, it's because we fill a balloon and we try to compress it, we can only go so far with that. And that's because the gas phase particles inside the balloon are exerting pressure on that inside surface. And so this pressure is defined as the amount of force spread through a unit area. Now, there are different measurements of pressure. In engineering, we tend to see pascals. 1 Pascal is 1 Newton of force per square meter. In chemistry, we tend to use atmospheres, which is equal to roughly 100,000 pascals, but it's a little bit slightly different than that, but about 100,000 pascals. And in weather reports, we tend to hear about inches of mercury. Now, in chemistry, we convert this to millimeters. And so 1 standard atmosphere is 760 millimeters of mercury. You may also see the unit torr. Torr is an equivalent to a millimeter of mercury. And you may wonder how mercury gets involved in this, and that's because it's related to the old atmospheric pressure measurements using barometers. Now, barometers are still around. However, more and more they've been replaced by electronic sensing devices. But where this whole concept of inches or millimeters of mercury came around was trying to measure air pressure. The atmosphere exerts pressure. Unfortunately, we can't really feel what that is because it's exerting the pressure on us from all directions simultaneously. But you can devise a barometer so that the atmosphere will only exert pressure in one direction, and that's when we can really measure it. So if you evacuate a lawn tube, cap it, and then submerge it into a pool of mercury, what will happen is that the atmospheric pressure can only press down on the pool of mercury from the top. And so that's going to force mercury up this evacuated tube, and you'll have this battle between gravity and the atmospheric pressure. And so they're going to be working in opposite directions. So when the gravitational force trying to bring mercury down the tube equalizes the atmospheric pressure, which is trying to push the mercury up the tube, when those equalize, you'll get a measure of the atmospheric pressure. And so one standard atmosphere is 760 millimeters of mercury. So that's the height of the mercury in the column. If we're in the lab and we want to measure smaller changes in pressure, what we use instead of a barometer is a device called a manometer. And there we have a gas sample, and then we connect that to a column of mercury that's trapped inside of a U-tube. And then we can look at the difference in the mercury levels between the open side and the side that's connected to our gas sample. And that difference corresponds to the difference in pressures. If the height of mercury is higher on the sample side, that means that the gas pressure of the sample is less than atmospheric pressure, and it's less by the height difference. If the mercury in the tube is higher on the atmospheric side, that means the gas pressure of the sample is larger than atmospheric pressure, greater than atmospheric pressure, by, again, the difference is the corresponds to the difference in heights. Now, there are several properties of gases that are interconnected. And so we're going to talk about pressure, temperature, and the amount of gas in volume. And so these properties were related to one another separately by several different scientists. And Boyle's law refers to the studies done way back in the 1600s between relating pressure and volume. And so I've got a nice little demo that I will likely bring to the workshop to show this. But basically what we do, if you want to compare what happens to volume as you change pressure or vice versa, you have to keep all the other factors constant. So you have to keep the temperature constant, and you have to keep the amount of gas constant. But when you do this, what you find is as you increase the pressure, the volume decreases. As you lower the pressure, the volume increases. And so that means that the product of pressure times volume is always going to be constant. Again, holding temperature constant and holding the amount of gas constant. And so we can write this mathematically. Pressure times volume equals a constant. If we're comparing pressures and volumes of the same gas under different conditions, that constant's always going to be the same. So the pressure and volume times volume at the first condition is going to equal the pressure times volume at the second condition. When we graph this, we find that this kind of inverse relationship gives this curve, where again, higher pressure, lower volume, and then as we lower the pressure, the volume will increase. And so this type of curvature and direction represents an inverse relationship between pressure and volume. Now, Charles' law is the study between volume and temperature. And if we keep pressure and the amount of gas constant, what we find is as we increase the temperature of a gas, it starts to expand. And actually, there's a good demo we can do with liquid nitrogen. I often do to demonstrate this. If you cool down a gas, its volume will shrink dramatically. And if you heat up a gas, its volume will expand. And in fact, it's these measurements that gave rise to the concept of absolute zero. So now mathematically, what we have to do is we have to put volume and temperature on the opposite sides of the equation. And then there's a proportionality constant that relates the two. And so if we want to compare volume and temperature conditions of the same gas under different situations, then we bring volume and temperature to the same sides. We have to divide. So the volume divided by temperature under the first condition will equal the volume divided by temperature at the second condition. This is a direct relationship. Now, as I mentioned, it's this relationship that gave rise to the notion of absolute zero, because if you plot the volume of a gas as a function of temperature, you get a linear relationship. Notice that positive slope, direct relationship, and you can take these trends and extrapolate them down all the way to zero volume. Now, of course, in actuality, if you lower the temperature of a gas enough, you don't actually get this zero volume because the gas liquefies. But in theory, you can extrapolate it to zero volume. And what scientists learn is that no matter what gas you study, they all extrapolate to the same temperature at volume zero. And it's this temperature that was defined to be absolute zero, negative 273.15 degrees Celsius. Now, another relationship between the volume of a gas and the number of moles is pretty straightforward. As you put in more gas, if the pressure doesn't change, then the volume has to increase. This is something very easy to demonstrate. Just blow into a balloon. Take a balloon, blow in a little bit of it, and then to demonstrate if you put in more gas, the volume expands, just blow in a little bit more. The balloon doesn't represent a perfect constant pressure situation, but it's close enough that students will get the point. And so that's, of course, shown here in this diagram. And the way that relationship works, again, it's another direct relationship. So volume is equal to a proportionality constant times the number of moles. And so, again, you can compare the number of moles and volume for a sample. Under one circumstance, it's going to be moles divided by volume equals moles divided by volume for the second situation, as long as the temperature and the pressure are still the same. Now, if we take all three of these relationships, we can bring them together, because you notice volume and temperature are directly related. So they're on opposite sides of the equation with a proportionality constant. Volume and number of moles are directly related. They're on opposite sides of the equation with a proportionality constant. Volume and pressure are indirectly related. So that's going to be PV equals the proportionality constant K. If we want to put volume and pressure on opposite sides of the equation, we have to divide by pressure. So what you can do is take all three of these expressions and put them together. And when we do, we get something called the ideal gas law. Pressure and volume are on the same side, and moles and temperature are on the opposite side. And this R is our proportionality constant for the whole relationship. It's called the universal gas constant, and it's equal to 0.08206 if we have liters as the unit for volume, atmospheres for pressure, and Kelvin for temperature, which we have to have Kelvin for temperature. So that's the ideal gas law, and I know at the middle school level you probably don't do calculations involving this, but at the high school level and college levels we do. Now, once we have those relationships, does anything change when we have a mixture of gases? And it turns out no. When we have a mixture of gases, because the gas molecules have such high energy contents, we can assume that they don't interact with each other at all. So if we have a fixed container and we add more gas, the pressure is going to go up. Well, it doesn't matter if the gas we started with is the same or different than the gas we add to it. The total pressure is still going to go up. And the idea is, and this is John Dalton, they confirmed this, that the total pressure inside the chamber is going to be the sum of the individual pressures that the individual gases would have exerted if it was alone in the container. So here in this cartoon, if we have twice as much gas A than we have gas B, then gas A would exert a certain pressure. Here we're saying 10, I don't know if it's 10 atmospheres, 10 torrs. Gas B would exert half that pressure, but then combine them together, and the total pressure in the flask is the 10 plus the 5 units. Now, experimentally, how can we collect gases? Well, the easiest way to collect a gas is to trap it underwater. And so kind of the idea is similar to what we would set up for a barometer, except we don't need to evacuate a tube. The way we do it is we take a tube or a jar or a flask and we completely fill it. we stopper it or cap it, and then submerge the top, turn it upside down, submerge the top into a pool of water. And then, of course, remove the stopper. And what happens is then if we have a process where we generate gas, then here, like for instance, if we heat potassium chlorate, that will actually drive off oxygen. It'll convert this compound to KCl. The oxygen is evaporated and is driven through this tube underneath the water and into the flask. Now, being a gas, the gas, of course, is going to float on top of the liquid. And so the oxygen will be collected at the top of this overturned jar, and then water will be forced out the bottom through, there's another hole here in the stopper. The key thing to remember is if you're going to measure the pressure of the gas that you collect, you not only have oxygen in here, but you also have water vapor. And it's a correction you can make. The water vapor pressures at different temperatures have been very well studied, very precisely studied. And so you can have students apply that as a correction. So, lastly, what we do, I like to relate some of this stuff back to the ABG test we were talking about. Normal carbon dioxide partial pressures in our blood is 35 to 45 millimeters of mercury. Normal oxygen partial pressures on the area of 75 to 100. If the results deviate from this, that means that we could have issues oxygenating our tissues if the O2 partial pressure is low, or if CO2 pressures are high, we could be asphyxiating our organs because we're not expelling the CO2 quickly enough. So there's some information about gases. I'll talk more and do some more demos at the workshop. And so one more lecture to go, and that'll be it for the series.